So limits at infinity take the form of the limit as x approaches infinity of a function f of x, or the limit as x approaches negative infinity of some function f of x. So limits at infinity is or are where the x variables are approaching either positive or negative infinity. Okay, so that's how you identify them. Now, there's something extremely useful to note. So if we have the limit as x approaches negative infinity of a function f of x, we can write that out as the limit as x approaches positive infinity of f of minus x. Let's just look at a quick graph to see why this makes sense. So if I had to draw a Cartesian plane, and let's say I have some function that looks like this, it looks like that, and it's going to approach 0 as we move more and more negative. Let's just make that clear. So let's extend it, and it's going to approach 0. So if I approach negative infinity, that means I go infinitely negative. Okay? The limit is going to be 0. But sometimes it may be a bit difficult to look at limits in terms of approaching negative infinity. It's really easy if we can approach positive infinity, as you'll see. Okay, so what we can do is this function is f of x. What we're going to do is we're going to take or obtain f of minus x. What's f of minus x? Well, if f of x is, let's say, x cubed minus x squared, how we get f of minus x is wherever we see x in place of the f of x function, write down a bracket. Okay, and in place of those brackets, you're going to substitute in minus x. Okay, so sub in minus x, and then just work out what that function is. It will be minus x cubed minus x squared. So this is f of x, and this is f of minus x. But more importantly, what happens when you go from f of x to negative x? What you're doing is you're changing the sign of x. So you are doing a mirror reflection about the y-axis. So this new graph here will look like this. So I think it looked like that, and then it will approach positive infinity. So this is f of minus x. So remember, when we approach negative infinity for f of x, that answer was 0. But now I'm going to approach positive infinity, or considering f of minus x. So we are going to approach positive infinity of f of minus x, and the answer is still 0. Okay, so that's a extremely useful trick that you can use. Also, the graph doesn't have to approach 0. I just used that for this example. We could approach any value. Okay, it could approach, let's say, 4. Okay, a y value of 4, a negative answer, and a y value of negative 12. Whatever the case may be, this rule will work. Okay, so just take note of that. Right, let's move on. Okay, so let's look at this. There are 3 important cases when performing this shortcut method, which I'm going to show you to solve limits at infinity. So there is a shortcut method to solve limits at infinity extremely quickly, and you just have to know 3 important cases. Before I go on to the cases, I just want to make sure that you understand what I mean by degree of numerator and degree of denominator, which you'll see here. So let's discuss what degree means. Let's get rid of all of this. Okay, so let's say I give you a polynomial, say x to the 7 minus 5x squared plus 3x cubed. And I ask you, what is the degree of this polynomial? Well, the degree is 7. But what is degree and how do I know it's 7? Okay, so degree is the highest power that the input variable, in this case x, is being raised to. I'll repeat that. When I talk about degree of a polynomial or the degree of something, I'm talking about the highest power that the x variable is raised to. Here we have a power of 7, a power of 2, and a power of 3. The highest power is 7. Let's just consider another example so that you understand it. If I say x to the minus 5, let's say plus x to the 3 plus x 0. What is the highest power, or what is the degree? The degree is 3. In this case, it wouldn't be a, let's not use -5. Let's say it's 2. There we go. The degree of this polynomial is still 3 because the highest power that x is being raised to is 3. One more example. If I say 7th root of x to the power 4 plus x to the power 3, what is the degree of this polynomial? Okay, so the answer is not 4. Okay, the answer is not 4. Why is that? Let's take a look at that. We can simplify that to root of 7, and then we have the square root of x to the power 4, so that's going to give us x squared plus x cubed. So this here simplifies to that, so the highest power, or the degree, is 3, it's not 4. Okay, so just take note about that. You need to simplify it. Now that we understand what degree means, let's move on to the examples, or the steps. So let's go for case 1. So these all deal with limits at infinity. Specifically, we're looking at when the limit or the limit as x approaches positive infinity. So these work with this case here. Remember, if you have negative infinity, you can always transform it using the rule I showed you on the previous screen. So if the degree of the numerator is less than the degree of the denominator, then the limit as x approaches infinity of f of x is equal to 0. Why? Okay, think about it. Let's say we have a simple term. Let's say we have x squared and x to the power 7. If you substitute, so we have x approaching infinity. If you substitute increasingly larger numbers into this function here, yes, this is going to get large, okay, because it's x squared. But this is going to get much larger, much faster, because it's x to the power 7. Okay, let's say you sub in 10, that's 100. You sub in that same 10 here, you're going to get a much larger number. Eventually, this is going to become so large that the function is going to approach a y, or it approaches a y value of 0. So that's why we have case 1. When the degree of the numerator is less than the degree of the denominator, the limit is going to be equal to 0. Okay. Then let's look at case 2, when the degree of the numerator and the degree of the denominator are equal. So what we are going to get is a fraction, and we have to take the numerator's leading coefficient and the denominator's leading coefficient. Okay, what's a leading coefficient? Let's say I have this polynomial, so let's say I have 4x squared plus 5x to the power 7. Okay, how do you identify the leading coefficient? Okay, ask yourself, what is the highest power? The highest power in this is 7. Let's circle that. And then to get the leading coefficient, you just have to ask yourself, what is the coefficient of this term with x to the power 7? Well, it is 5. And that's how you get the leading coefficient. Let's just do one more example to ensure you understand. So we'll have negative 3x squared plus, let's say, 2x. What's the leading coefficient? Well, what is the highest power? The highest power is squared. Here's the term with the highest power. There's the coefficient of that term. The leading coefficient is -3. So that is what a leading coefficient is. Okay, so all you need to do is identify the leading coefficient in the numerator and then divide it by the leading coefficient in the denominator. That's when the degree of the numerator is equal to the degree of the denominator. Okay, let's look at the third and last case. The degree of the numerator is greater than the degree of the denominator. So your answer is going to be equal to either positive infinity or negative infinity. And I'll show you in some of the examples how you identify whether it is positive or negative. Okay, whether it's positive or negative infinity, that will depend on the function. Okay, let's just think about why this makes sense. So the degree of the numerator is going to be greater than the degree of the denominator. Let's say I have x to the power 7 over x squared. Let's say I'm going to positive infinity. This is going to get, okay, so let's look at the x squared. That's going to get large, but this is going to get much, much, much larger, okay, and much faster. So we have a very large number over a slightly large number. Okay, so your answer is going to approach positive infinity, or if there's a negative sign here, this is going to approach positive infinity, but because you have a negative in front, you're going to approach negative infinity. That's why this answer here is dependent on what sign you have in front of all these terms. And I'll show you an example that covers that. Okay, let's just go into some more notes. Note that in either case, if either case 1 or 2 occurs, the function will have a horizontal asymptote at that limit value. So if you have case 1, case 2, you're going to have a horizontal asymptote at 0 or horizontal asymptote at whatever that fraction simplifies to. And this is going to be very useful when you are covering graph sketching. Okay, so just take note of that for graph sketching. Note that a function can have 2 possible horizontal asymptotes, as it is not necessary for the limit as x approaches infinity to be equal to the limit as x approaches negative infinity of f of x. So these two basically do not have to be the same. And think about it, you can have some functions that look like, let's say that one is approaching 0, and this one is going to approach 10. As you approach negative infinity, it's going towards 0. As you're approaching positive infinity, it's going to approach 10. So these two limits do not have to be equal. All right, let's go on to some examples. So let's solve these limits at infinity using the shortcut method. There is a long way of doing it, but for this video, I'm just going to explain the shortcut method and apply the cases that we had in the previous screen. So let's take a look at this. The degree of the numerator is 2 because that is the highest power that the x variable is being raised to, and the degree of the denominator is also 2. So the degree of the numerator is equal to the degree of the denominator. We are dealing with a situation of case 2. In that case, we take the numerator of the leading coefficient. So, or we take the numerator leading coefficient rather. Okay, the leading coefficient in the numerator is positive 3. So that is going to be 3 over, and then we look for the denominator leading coefficient. That is going to be 4. Okay, so we have 3 over 4. And that's your answer. That's all you have to do for the shortcut method. Okay, so that's how you handle it. Just in case you're wondering how I found the leading coefficients, in case you didn't understand, look at the numerator. We have 3x squared plus 4x minus 5. We know that the degree is 2. Where is that degree found, or what is the term with the highest power? So that's the 3x squared. What's the coefficient of this term? It's 3, and that's how I got the leading coefficient. And then you just have to apply that for 4x squared minus 109. 4x squared is the term with the highest power, therefore the coefficient is 4. That's the leading coefficient. Okay, that's how you handle this example. Let's move on. All right, take a look at this, identify the case, and try to solve it. All right, let's look at this. So this is a situation where the degree of the numerator is 5, and the degree of the numerator, the degree of the numerator is 5, and the degree of the denominator is 2. So in this situation, we have a case 3, and just a word of advice, I wouldn't try and memorize the cases. If you understand what happens when the degree of the numerator and degree of the denominator is smaller or larger compared to each other, then you should be fine. You don't need to memorize case 1, case 2, case 3. Okay, so you can identify this as a case 3, but basically degree numerator greater than the degree of the denominator. In that case, we are going to approach positive or negative infinity. So our answer is going to be plus minus infinity. How do we decide whether it's positive infinity or negative infinity? What we have to do is look at the leading coefficients. So let's look at the fraction. So the leading coefficient in the numerator is going to be 3, and for the denominator, it is going to be 4. So this will give us a fraction of 3 over 4. 3 over 4 is a positive fraction, so we will choose positive infinity. So this answer is equal to positive infinity. If, for example, let's say, for example, the leading coefficient was negative 3, so we had negative 3 times x to the power 5, we would have negative 3 over 4 as our fraction, then we would have a negative fraction and we would choose negative infinity. So that's how you identify it. You take the fraction of the leading coefficients, but for this one, it's positive. All right, let's move on. Okay, take a look at example 3. You know what to do here. Apply that little trick I showed you, and you should be good. Okay, let's go for it. So what we're going to do is we're just going to rewrite this as the limit as x approaches infinity. And wherever I see x in this function, I'm going to substitute in negative x. If you do that substitution, you are going to obtain this function. So you'll get minus 3x to the power 5 plus 30x minus 6 over 4x squared minus 4. Okay, so just take a minute and make sure you're happy with that. Now we can work with this because it's limit as x approaches infinity. So the degree of the numerator is 5 and the degree of the denominator is 2. So we can see that this is going to approach either positive or negative infinity. We're dealing with a case 3 here. How we decide whether it is positive or negative infinity is we have to look at the fraction or ratio of the leading coefficients. So the leading coefficients are minus 3 over positive 4. This is a negative fraction, so our answer is going to be negative infinity. And that's how easy the shortcut method is.